Assalamu alaikum. Today, I would like to discuss one of the most elegant and powerful algorithms in numerical methods, that was the Newton-Raphson method. While there are many ways to find the roots of a function, so Newton's method stands out because it doesn't just search blindly. It uses geometry of the curve itself to find the answer with incredible speed. So before getting started, let me introduce myself. I am Tanvir Islam. My ID is 2102043 and my registration number is 10170. Let's start with the fundamental problem. In introductory calculus, we solve equation where x is easy to isolate. But in real world, like engineering, whether it's fluid dynamics or electrical technology or electrical circuit, we constantly face nonlinear equation where algebraic isolation is impossible, or we cannot find the exact analytical solution. We must approximate it, while methods like bisection or false position or anything offer a safe but brute force approach. They are computationally expensive, so we need something smarter. So writing the tangent, this is the core intuition of Newton-Raphson. Instead of gauging a range, we start with a single point x naught, and we calculate the derivative at the point and draw the tangent line. So the logic is simple. The tangent line is a good local approximation of the curve. Therefore, the root of the tangent line should be good approximation of the root of the curve. So we need where the line hits zero and becomes our new starting point. We are effectively surfing the derivative down to the solution. So going to the next slide, that was the iterative formula, where we can see xn plus 1 equals to xn minus f of f function of xn by derivative of function of xn. So new position equals old position minus the function value over the slope. It is elegant because it is self-correcting. If the slope is steep, we take a small step, and if the slope is shallow, we take a larger step. So the mathematics naturally adjust the step size based on the behavior of the function at the exact moment. So the algorithm is straightforward to the implement programmatically. That first we initialize a reasonable starting, then we iterate through loop, updating the for updating x and termination. We when the change between steps drops below our error tolerance, usually 10 inverse or 10 to the power minus 6 or smaller. It is a loop that defines itself with every passes. So, quadratic convergence means why do you prefer this over the bisection method? The answer is convergence speed. So, bisection has linear convergence. It gains roughly 1 bit of accuracy per step. Newton-Raphson exhibits quadratic convergence. Roughly speaking, the number of correct decimal places doubles with every iteration. If you have two correct digits now, you will have 4 in the next step, and then 8, and then 16. It rushes toward the solution. So critical limitation means, however, as engineer, we must understand the failure modes. This is not a magic bullet. First, if the derivative is 0, a horizontal tangent, the formula divides by 0 and the algorithm crashes. Second, if our initial guess is too far away, our or near an inflammation or inflection or near an inflection point, the tangent line can actually short us away from the root, causing divergence. It is powerful, but it requires a good neighborhood to start in. So let's dive into the application of the Newton-Raphson method. So firstly, we can see the computer graphics. To prove this is not just theory, let's look at the computer graphics. Lighting engines need to normalize vector constantly. which require calculating 1 by root over x, standard 1 by root over x, standard square root operations are too slow for real-time rendering. The famous and first inverse square root algorithm used in the Quark engine utilize a single iteration of Newton's method. It provides enough accuracy for lighting physics instantly, allowing games to run at high frame rates on limited hardware. So let's look at the next slide, and that was the computational finance. In finance, we use it for Black-Scholes models, and traders often know the price of an option and need to find the implied volatility, the market's expectation of future risk. There is no algebraic formula for this. Every time you see a volatility index updating a real time on a trading terminal, there is likely a Newton-Raphson solver running in the background, converging on that value in microsecond. In conclusion, Newton-Raphson offer unrivaled speed with its quadratic convergence. It leverages calculus rather than just interval chopping from rendering 3D worlds to pricing assets. It is the workshop of modern numerical computing.